Hello everyone, welcome back to my channel. So today I'm going to share one of the interesting paper talking about the lithium ion phosphate, uh, the lithium ion phosphate battery capacity fading mechanism. This work is published in a Chinese journal. This one, the main content is in Chinese, so I'm gonna explain the I'm gonna try to translate the content to you. So this paper title is Analysis of the Capacity Fading Mechanism in Lithium Ion Phosphate Power Batteries Cycled at Ambient Temperature. This work is done by collaboration with Institute of Nuclear and New Energy Technology, the Tsinghua University, and the CATL company. So the main content of this work, as you can see from the title, LFP battery capacity fading mechanism in ambient temperature. So let's jump into the how they did and what they find. So what they use for the study is the CATL cell. They're using the 240 amp hour cell in the same batch, and then they cycled in 1C 25 degrees C for the cycling, and the cycling voltage is 2.5 volt to 3.65 volt. So I will highlight the major specs or major informations. Then you can find later. I will share this paper in a link. They were also using a fixture for applied pressure and also monitor the expansion of the cell. The initial external force is 300 kgf. It's roughly like I'm not sure what the PSI is, but it's like 300 kfg, 300 kfg. And then they cycled using the Newell tester, the CT 802/5 volt, 300 amp, and they're using the stainless steel plate with thickness of 15 millimeter. Some like the force sensor, the the membrane chamber brand. So they were using several cells with the same batch, and so what they will do is at different SOH, like SOH in 88%, 84%, and 80%, and then they will disassemble that at a voltage of 2.5 volt, and then using the DMC to eliminate one side of the material, and then dry it, and then using those kind of the single side coated anode and cathode to make the coin cell with a separator. So they will punching the electrodes to 14 millimeter diameter, the disc, and then using the 0.6 millimeter lithium foil for the reference for the counter electrode, and 15 millimeter the cell gas separator for this coin cell, for this half cell. And then they were using So what they said for this one? Okay. So another so this is a half cell experiment, and then another part of the experiment is they will they will again using the DMC to wipe out the one side of the material, both anode and cathode, and then for anode side, for cathode side, they will making the 42.5 times 49 times 49.5 millimeter the cathode, and then the anode is larger than the cathode, is 44 millimeter times 51 millimeter, and then sandwich with a cell guard separator. So they will sandwich these single layer single coated cathode and single coated anode with a separator to make the single layer full cell. And then they were using the 0.04 millimeter copper with plated lithium as a reference electrode. So I will explain a little bit here. So for the reference electrode, in the fabrication of this full cell, they will only use the 0.04 millimeter copper wire, and during the testing, they will plate the lithium on the copper wire first. So this process is for making the plated lithium on copper wire as the reference electrode, and then they were using this one as the reference electrode for this full cell. Okay. And then their electrolyte is ECDMCTEC solvent in the 1 molar per liter LiPF6 electrolyte. For the coin cell, for half cell of the cathode side, they will cycling at 2 volt to 3.75 volt with the cycling current is 0.1 C. For the anode side, the half cell, they will cycling in 0.0005 volt to 2.0 volt with 0.05 C with C over 20. For the half cell, 3 electrode half cell, for the 3 electrode full cell, the stacking one, here with a plated lithium on copper wire, they will use that during the EIS measurement, and the EIS measurement is 10 millihertz to 100 kilohertz with 5 millivolt voltage. So next part is the result of their study. So in figure 1A, B, and C. So figure 1A is the cycle number versus a capacity retention. You will see initially decreasing faster, and after when it reaches around 95%, it reaches steady state, slower decreasing rate. The figure 1B is the cycling, it's a cycle number versus the average with the average voltage difference. There is not much differences during the cycling. And so figure 1C is capacity retention versus the versus the expansion force, the maximum expansion force during the cycling. So before 92%, around 92% of the capacity retention, the maximum expansion force is around uniform, not uniform. It's around not change too much. This is because the cell, when it designs the cell, it has some buffer for the cell to expand. So you will see some like non-change region. After that, the maximum expansion force is roughly linearly grows. So this is a summary of this testing. And then the second part is figure 2. Figure 2 is analysis of capacity fading in batteries with different SOH. So they have 4 figures. The figure 1 is the charge discharge curve, charge discharge capacity voltage curve at different SOH. And figure 2b is the DQDV curve versus voltage curve at different SOH. The figure 2c is a so in figure 2b, there are 3 major peaks for the DQDV curve, and then in figure 2c, for each peak, the red one is a so the first peak on 3.3, they were showing the peak area with amp hour versus SOH, and peak 1 is 3.3, and in here is labeled with black dash dots. Peak number 2 is around 3.4 volt. In the figure 2c, that is in labeled in red dash line. The peak number 3 is around 3.45 volt. That is in the blue dash dot plot trace. So in figure 2D, that is the peak area losing rate versus SOH for different peaks. So it's basically transfer this value to the percentage of the loss. So you will see in figure 2b, the QDV curve, the 3 peaks has some like shifting, and also in figure 2c, you will see the peak area has some changes. Figure the black dash dot, which is a peak 1, generally not changing too much. Peak number 2, which is a 3.4 volt in red dash dots, slightly drop during 90% to 80%, and peak number 3 in blue dash dots, which is in 3.45 volt. This is a major decreasing peak. So you will see the major peak area loss is peak number 3. So peak 1, 2, and 3, they so here they have some conclusion is the capacity fading is coming from the loss of active material and the loss of lithium inventory, since the active material in the anode side, which is graphite side, peak 1, 2, 3 all belongs to that graphite. You will see peak 1 and 2, they are decreasing around like 10%. So so it's like in this anode material, when the anode material losing like 10%, all three peaks will losing 10%, and you have extra, so you have total in like around 60% of the losing for peak 3, so which means you have another around like 50% loss coming from the loss of lithium inventory. So which means the loss of lithium inventory is a major contribution to the capacity fading in these LFP cells. So this is their analysis for this part. And then the figure number 3 is a half cell. So the charge discharge profile of the half cell. So they basically extract the half cell and they eliminate one side of the material and then pair with silicon foil to do the charge discharge at different SOC. You see no big difference for the for the cathode side in figure 3A. You will see in figure 3B, this is anode side half cell. So they have the zooming image. So they basically trying to point out the over potential increasing like 5 millivolt near the end of the charge discharge region. So their claim or their they want to point out is this 5 millivolt is somehow the major contribution for the kinetic or for the rate performance decreasing from anode side. What they have done later is they will do some other present other data to prove to give more evidence to this kind of discussion. So what they have done is it's a single layer full cell. Actually, it's a single layer 3 electrode cell. So they do the EIS measurement for those 3 electrode full cell, for those 3 electrode cell. And the figure 4A is the cathode side ES data. You barely can see no obvious no big difference for the charge transfer resistance, and also the shapes differences for the cathode side ES during the different SOH. And the figure 4B is the anode side, the graphite side ES during the different SOH. So you'll firstly see the ES shape changing from 88% to the following capacity retention, and then after 84% to 80% capacity fade, the charge transfer resistance also change a lot. So which means in their data is the charge transfer resistance changes mostly in the anode side after capacity fading. So this is another supporting evidence for their claim. And then another experiment they have done is they're doing EIS with or without external pressure. So figure 5A is so all the black all the black data is without pressure. The red data is with pressure. So I will explain the first two figures first. So figure 5A is the cathode part. Yes, with external pressure, there's not too much change compared to the no external pressure. So cathode part, the pressure won't influence the impedance too much. So in figure 5B, that is a graphite side. Yes, you will see without pressure, external pressure, you will see some the similar data as the 88% thing, the shape. And then after you apply the pressure, you will see the shape changes and the charge transfer resistance increasing after the pressure has been applied. So which means the figure 5C is the separator side. You starting from 0.4 megapar, the black dot data. The red is 0.8 megapar. The blue dot is 1.2. The orange one, the yellow one is 1.6 megapar. So the separator part, you will see the plot shifting to left side for the first point, which is an internal resistance part, rather than the charge transfer part. So the major charge transfer part differences between the external pressure and without external pressure is coming from the anode side. So this is another support for the argument that during the cycling, the rate performance differences is mainly come from the anode side. So that's it for this paper. I will share this content and then give you the link for download this paper. Thanks for your watching. Thanks. See you in next video.